Okay, so I want to explain now this Iwasawa's proof of, it'll take, to cover all the aspects, will take most of the rest of my lectures, but the key ideas in some sense will already emerge today. That's what I want to talk about. So for the moment, what I want to assume, I hope that's clear to everyone, I've got F will be an arbitrary finite extension of Q, and F infinity at the beginning will be any ZP extension of Q. Only later will I assume that it's the cyclotomic one. And as usual, gamma will be the Galois group of our extension. And I want to mention to you this important fact that the only places of F which can ramify in F infinity must be the finite places dividing P. They must divide P. Not all of them will necessarily ramify at all. At least one must, of course. And that even includes the infinite places. And the reason for that is simply that the global class field theory would tell you that the inertia group of any prime which doesn't divide P, it must be a finite group in this abelian extension, and ZP has no closed finite subgroup. So that's why only ramification can occur at the primes dividing P. So now what I'm going to be interested in, so I've got my arbitrary ZP extension, is this field M infinity here, which by definition is the maximal abelian P extension of F infinity. That's the top of the ZP extension, which is unramified outside P. So you only allow ramification at the primes of F infinity dividing P. And then I'm going to be interested in the Galois group XF infinity of M infinity over F infinity. So I've just made this little diagram here that we have M infinity, this Galois group, I'm calling it his gamma here. And now the key observation, of course, is that by maximality, M infinity has to be Galois over F. Of course, it won't be abelian at all, but it has to be Galois over F. And so that means that we have the exact sequence of Galois theory. Naught goes to XF infinity, goes to the Galois group of M infinity over F with quotient gamma. This is always the standard situation that you have in classical Iwasawa theory. And then automatically gamma operates on the abelian group X of F infinity simply by lifting elements, right? If you have a tau in gamma, you lift it to a tau tilde in the Galois group, any lifting in the Galois group of M infinity over F, and then you define the action of tau on an element of X of F infinity by this tau tilde x tau tilde to the minus 1, by this inner automorphism with tau. And the only observation you have to make is that because X of F infinity is abelian, this is well defined. So this is the action that you are always studying in classical Iwasawa theory. And so now the crucial question that we want to study is what is the group of gamma n remember gamma n is the unique subgroup of index p to the n. What is the index, what is this group of X of F infinity gamma n, the gamma n co-invariance? Well, by the very definition of this action here, that if you think about it for a moment, when you take co-invariance, the taus will now be in gamma n, and then if it's the minus 1 actually just corresponds, I mean, if it's a topological generator minus 1, the minus 1 will just add another thing there to make a commutator. And so what you see immediately is that, in fact, this x of f infinity gamma n has to be the Galois group over f infinity of the maximal abelian extension of Fn in M infinity, because remember, gamma n is the Galois group from f infinity down to Fn. And now there's a basic little lemma here in this special case. You see, after all, Mn, it's the maximal abelian extension of Fn contained in M infinity. It must always contain F infinity, because the only ramification in F infinity over F is by primes above P. When we come in the last lecture to look at the unramified analog of this, then that will no longer be true. But here, and so a moment's reflection tells you that in fact M of n, that is the maximal abelian P extension of Fn unramified outside P. You can forget the F infinity if you like. So all of this is simply because the only primes which can ramify in F infinity over F must divide P, and the Galois group we're looking at is the maximal extension unramified outside P. So, now, but now you see that tells us that because of this fact here, we know from the class field theory, from classical global class field theory, the ZP rank of the Galois group of Mn over Fn. This is what I was talking about at the end of last lecture, but I just talked about it for F. Namely, it will be, in fact, I just talked about the rank of the closure of the units, but it will be, to calculate the rank of the Galois group, you have to take the rank of the local units, the product of the local units at the primes above P. So that is R1 plus R2 for Fn, and R1 plus 2R2, and then you have to subtract off the part coming from the closure of the units. And so what you see then, if you do that immediately, is this statement here that the ZP rank of the Galois group of Mn over Fn is the R2 for the field Fn plus 1 plus the Leopold defect, because for the field at P, for the field delta Fn, right? Because we're looking at the quotient of the local units modulo the closure of the global units at this level of this field Fn. So actually, we're not so much interested in how big the Galois group of Mn over Fn is. We're interested in the Galois group of Mn over F infinity. But the rank only drops by 1, doesn't it? Because we know that the Galois group of F infinity over Fn has ZP rank 1 because it's isomorphic to ZP. And now what is this? R2n is the number of complex primes of the field Fn, and the field Fn is an extension of degree p to the n of F. And remember, you can't have real primes becoming complex primes. That's forbidden for a ZP extension. And so, in fact, we see immediately that R2n must be just R2 times p to the n, because every complex prime is just going to split completely when you go up. So finally, we end up that the ZP rank of XF F infinity gamma n coinvariance is R2 p to the n plus delta FNP. And now, if you remember that what comes out of these algebraic structures, see, x of f infinity is a finitely generated lambda gamma module. Now we use a structure theory for lambda gamma, of course, is the Iwasawa algebra. And the structure theory tells us that, in fact, if R, say, was the rank, then we would get here that this would, taking the gamma n covariance, when n is sufficiently large, would give us p to the n times the rank plus some constant. So we immediately conclude from this estimate, this calculation of the rank that we've carried out here, that I've done here, that x infinity must have lambda gamma rank greater than or equal to R2, firstly, always. And secondly, that it will have a lambda gamma rank exactly equal to R2 if and only if the delta FNP are bounded as NF tends to infinity. So this holds for any ZP extension. And unfortunately, we don't know how to prove in general yet that the delta FNP are bounded as n tends to infinity for an arbitrary ZP extension. This is unknown. In fact, we only know it for the cyclotomic ZP extension, and I'll be explaining Iwasawa's proof. But I want to make one little remark that I leave to you as an exercise to think about, but that if we knew it at the bottom, or in fact anywhere up the ZP extension, that the Leopold defect is 0, just once, then because of this argument with the Iwasawa theory, it would follow that it then has to be bounded all the way up. That's a little exercise with the structure theorem to see that. So now that goes there, and I guess this goes here. So this is Iwasawa's theorem now, that assume f infinity over f is the cyclotomic ZP extension. In other words, the unique ZP extension in f, which you get by inside which it lies inside the field of f adjoin all p power roots of unity. Then if we're in this situation, in fact, it is true that the delta Fn are bounded as n tends to infinity. We're going to prove that. And therefore that the rank is exactly R2. And well, for those who are sort of interested in the project, I mean, there are other ZP extensions for which hopefully one might be able to attack this, but at the moment this is the only one that we know. So the whole idea, how we're going to exploit that it's a cyclotomic ZP extension, is to use multiplicative Kummer theory. And in fact, I want to assume that for the argument that mu p is the piece roots of unity is contained if f is p is odd, and the fourth roots of unity if p is 2. So this tells me that my f infinity must actually be f adjoin all p power roots of unity. Now it's perfectly true that to prove Iwasawa's theorem you have to then carry out a little additional argument to show that once you've got it in this case, you've got it also in the case without this hypothesis and the cyclotomic extension. I'm not going to go into that. It's almost obvious for p odd. For p equals 2, you have to say perhaps a little bit more. So how do we exploit the existence? Well, the whole idea is that we're going to use classical multiplicative Kummer theory. So let me remind you what it is that we're going to use. So I'm now F infinity abelian will be the maximal abelian P extension of F infinity without any conditions on ramification. Just take the largest possible, but P extension. I don't want to look at non-P extensions. And then the Kummer pairing is a pairing between the Galois group of F infinity abelian over F infinity and the multiplicative group of F infinity cross tensored over Z with QP mod ZP into the group of P power roots of unity. Let me just remind you, I think you all know this, that if you have a sigma in this Galois group and you have an element here alpha tensor P to the minus A mod ZP, then it's to get the P power root of unity attached to that pair, you take any P to the 8th root of alpha, and then you look at sigma beta over beta. Beta is this root, and that will be a P power root of unity, and it's sort of more or less trivial to verify that this is a non-degenerate pairing, so that it as a abelian groups, we have this compact abelian group, the Galois group of F infinity over FAB. We get the induced isomorphism of that as the homomorphisms of this discrete P primary abelian group, F infinity cross tensor QP mod ZP into mu P infinity. That's what the pairing tells us. And in addition, I mean, remember, gamma is acting on all these groups, and it tells us that it preserves the natural action of gamma. So now we want to look, but we're not interested in the Galois group of, I mean, it's far too big as an Iwasawa module to be interesting, of F infinity abelian over F infinity. We're interested in the Galois group of M infinity over F infinity, where we only allow ramification at the primes dividing P. And so we have to ask, what will be the Kummer? So by Kummer theory, I mean that Galois group here, it's a quotient, of course, of the other Galois group. It will be the homomorphisms of some subgroup, which I'm going to call Gothic or round M infinity, of F infinity cross tensor QP mod ZP. It will be just the homomorphisms of this subgroup into mu P infinity. And so I have to tell you now what is M infinity. I have to explain exactly what it is, and it's very easy to see in this case. The first thing we should remark is that, which is not true again for an arbitrary ZP extension, but for the cyclotonic ZP extension, there are only finitely many primes above any given finite rational prime. This is a little exercise. You check it first for the field Q adjoin mu P infinity. Even though this is an infinite extension, there are only finitely many primes there above any rational prime. And then it's a little exercise. Once you have it in that case, it extends trivially when you translate the whole thing by a finite extension. So therefore, we can talk about the... And by the way, the other thing is that if I look at just the set of primes which do not divide P, they are all discrete. They're only, I mean, I can take the free abelian group on those primes, and it will be the natural divisor group. So therefore, what we conclude is that I'm going to write I infinity prime for the free abelian group on the primes of F infinity which do not lie above P. But by the way, I'm not, oh well, of course, every prime above P here is ramified anyway. And therefore, if I have any alpha in F infinity cross, that should be not prime, I can talk about its ideal alpha prime in this I infinity. Makes perfectly good sense. And so what I now want to do is to tell you that M infinity is the following group. You look at all the elements alpha tensor p to the minus a mod zp in F infinity cross tensor qp mod zp, such that the ideal, the prime ideal of alpha, actually is, in I infinity, is a p to the 8th power. Now, I mean, I'm not going to, this lemma is essentially obvious. If you're not going to remember these, in I infinity prime, the ideals that occur are those which do not divide p. So that if they don't ramify when you take the p to the 8th root of alpha, then you must have this condition. That one way is obvious and the other way is almost as obvious. So that's what the M infinity is. And now we're going to be interested in inside of F infinity, there's also the group of P units, if you like. So by definition, these are the set of all elements alpha in F infinity cross whose prime ideal is 1. So they are the, if you like, the units of the P integers of F infinity. Of course, they form a multiplicative group. I haven't as yet tensored them with QP mod ZP, but now let me do that. So I guess this goes there. And you see, if I tensor them now with QP mod ZP, that I will get a natural map I infinity to M infinity, because clearly anything in here, because its prime ideal is 1, that when we look at it inside M infinity, when we look at it inside of F infinity cross QP mod ZP, it will be inside M infinity. Now you need it's a sort of essentially obvious, I'll leave you to think about it, that this map here, I infinity, is injective. There's no problem about that. So this enables us to think of this E infinity prime tensor QP mod ZP as a gamma submodule of M infinity. Now, there is a second map, J infinity, that I want to describe, namely, let's let A infinity prime be the P primary subgroup of the ideal class group of, now I take I infinity prime modulo the group of all the prime principal ideals. That's exactly the same, by the way, if I looked at finite levels, if I took the same group, the analogous group at finite levels, and then took the inductive limit as you went up the tower. This is something that someone was talking about this morning. Romya. It's exactly the same object. And you see, I have a natural map from M infinity to A infinity prime, because remember, M infinity, this is the map which we had yeah, I haven't written it down. Maybe I should. Let me just write it down. I mean, it is the obvious map, but let me write it down. Here, so I mean, the point is that J infinity of, let me stick to my notation, alpha tensor P to the minus A mod ZP is the class of A, of Gothic A, where in fact alpha prime to the p to the t, sorry, where Gothic A is the class of, now how shall I put this? Sorry. Well, I will have that alpha prime, that principal ideal, has to be a p to the 8th power, because we saw that was the very condition that defined the non-ramification, and so I send this to the class of this A here. So that's a p-primary class in the ideal class group. So that leads, therefore, to you get this sequence of gamma modules. Naught goes to E infinity prime tensor QP mod ZP, where that's the map here is the I infinity, and the map here is the J infinity. And again, it's a trivial exercise. It's essentially the same as if you were doing at finite levels to check that this sequence is exact. But now you see the fact that it's exact, that enables us to break up our ZP extension, our unknown extension of M infinity over F infinity into, we're going to define, I'll write it again in a moment, we're going to define M infinity, this intermediate field N infinity prime, F infinity here, and it's the obvious thing that you take, namely you take N infinity prime to be the field that you get by joining to F infinity the p to the nth roots for all n of all epsilon in E infinity prime. This is the field that you get. And because of this exact sequence, because we have the exact sequence there, if you think about it for a moment, that we therefore end up with this, so we have this tower here, M infinity, N infinity prime, M infinity, where this fellow, by Kummer theory, is the Galois group of N infinity, is the homomorphism of E infinity prime tensor QP mod ZP into mu P infinity, and therefore this Galois group of M infinity over N infinity prime is the homomorphisms because of the exact sequence of A infinity prime into mu P infinity. You see, it's precisely this breaking up of the extension, which we can do here in the Kummer theoretic situation, there is no analog of this. There's no known analog for other ZP extensions. This is what underlies the whole argument. So now you see, of course, we're interested in the lambda gamma rank of the whole of the Galois group of M infinity over F infinity. But that will be the lambda gamma rank because we now have the exact sequence coming from these of this part plus the lambda gamma rank of that part. Right? And so now I'm going to state the two theorems that Iwasawa proved, which answer both these questions. And the first one is, let me talk about the lambda gamma rank of M infinity over N infinity prime. In other words, the lambda gamma rank of this object here. Now, in fact, Iwasawa's proof of the result I'm going to state works for an arbitrary ZP extension. The only point you have to make is that for an arbitrary ZP extension, he actually proves it for an arbitrary ZP extension, because you can't talk about an arbitrary one, gamma acting on mu p infinity. You have to replace the mu p infinity by QP mod ZP. But you see, this really changes nothing, because this is just corresponding to a Tate twist that various people have already been talking about, right? That if the homomorphisms from A infinity prime modulo QP mod ZP, if this is a torsion as a lambda gamma module, certainly it will be when you take its Tate twist by any number of times. We'll just take one, which is the homomorphisms from A infinity prime to mu infinity. So I will talk about the proof of theorem A, which is, as I say, true for any ZP extension in my last lecture on Monday. But now, what about the other one, namely the Galois group of n infinity prime over f infinity? And in fact, this is Iwasawa's theorem that assuming mu p infinity is contained in f infinity, then the Galois group of n infinity prime f over f infinity is a finitely generated lambda gamma module of lambda gamma rank R2. And by the way, it's not 2 here, it's divided by 2, right? Because remember, because mu p infinity is contained in f, this means that the base contained in f infinity, the base field f must either contain mu4 or mu p, so it's totally imaginary. So the R2 will be that, and so this is what we're going to prove. That's theorem B. In fact, I should say now that I probably won't have time to go into it tomorrow, but Iwasawa's proof of this theorem is, in fact, remarkably simple, but in addition, it also completely determines, I probably won't spell out the details, what the torsion submodule of this Galois group of n infinity prime over f, the lambda gamma torsion submodule is. It's a finitely generated ZP module, and you can say exactly what its characteristic element is. This also comes out of the proof. And there are other things that come out of the proof, which I'll say something about perhaps tomorrow or on the last day, to do with there's an interesting question about finite submodules that will emerge when we talk about this. So there is no finite, sorry, let me correct that. There is, Iwasawa proves there is no finite submodule in this Galois group, but it's a question of whether or not it's free. It modulo its torsion submodule is free. And there is an interesting finite group that emerges. So in fact, I want to now talk a little bit about the first ingredient in the proof, which is something which is not quite obvious a priori, and which is certainly true, I think, in general for elliptic curves and abelian varieties, where it's also not quite obvious. But I'm only going to talk about this case in the situation that we want here. So what I want to look at now is some elementary properties of the groups En prime, that's these prime units at level n, and E infinity prime, which is the prime units up the top. And what I want to do is I want to get rid of the torsion in them, so I'm going to write Wn for the group of roots of unity in Fn, or including n equals infinity. So for F infinity, it'll be mu p infinity times some other group of order prime to p, and then at finite level it'll be a finite group. So I divide out by those, and I write now these script En primes and script E infinity primes for the corresponding groups, which will now have therefore no torsion. Right? Now, the first thing that we know is that by the theorem of Dirichlet's theorem generalized slightly by Chevalet to S units, to prime units, we know what the exact, that this En prime is a free abelian group, and we know exactly its rank. It's totally unlike elliptic curves. That's exactly, we don't know any analog of that sort of situation. But in any case, we still have finite generation then. And so the theorem of Dirichlet-Chevalet is that for every n, every finite n, E infinity prime is free of rank R2 p to the n plus Sn minus 1, where Sn is the number of primes of the field Fn above p, because they're all ramifying. We're taking them all in the prime. This should be W infinity here. Yeah, you're absolutely right. Thank you. Yeah, it should be W infinity. I'm sorry, this is just a misprint. Yeah. Okay, so what is not obvious a priori, now let me move this over, is that E infinity prime is, of course, it's a torsion-free abelian group, but what's not quite obvious is, and it's, of course, E infinity prime will be the union of all the En primes, but it's not obvious that it will be a free abelian group. That's the remark we have to make. But the little lemma that I'm going to prove now is that it is. This was remarked by Iwasawa. So there's the lemma that, in fact, E infinity prime is a free abelian group, and for every n, En prime is a direct summand as an abelian group. So how do we prove this? Well, of course, it's obvious from Galois theory that E infinity prime fixed by gamma n is En prime for every n. And let's also note that H1 of gamma n W infinity, which is by definition of the H1 the gamma n co-invariance of W infinity, that is always 0. I mean, the non-p part contributes nothing, and the p part, this is sort of one of these basic lemmas. You want to look at the I mean, you've got well, I leave it to you. There's a little exercise in which basically the simplest proof is that if you have a map between vector spaces, finite dimensional vector spaces, which is injective, then it must be surjective, a map of this in the same space. So therefore it follows from knowing this and knowing this that the curly E infinity prime gamma n for every n is En prime, curly En prime, that the same identity holds at level n for all n. Now the next observation is that since E infinity prime is the union, let's recall that E infinity prime is the union of all the En primes, and the key remark is that E infinity prime over En prime is torsion free. Now, why is that? This is because if you had a u in E infinity prime whose case power was in En prime, then, in fact, if you took a gamma in gamma n, we would get gamma, it's a u, gamma of u over u to the power k was 1, but there's no torsion in E infinity prime, so that tells me gamma u is u, and since E infinity prime is torsion free, we would get that u is in E infinity, in En prime. So there is no torsion. That's the point. And in particular, Em prime, mod En prime, is torsion-free for all m greater than or equal to n. It's just a special case of this. Therefore, but they are finitely generated abelian groups, right? And therefore that one will be, because it's torsion-free, the En prime will be a direct summand as an abelian group of the Em primes. And now you just keep doing this as you go up the tower, and you get what you want. So this basic fact is going to be very important in that, my gosh, I've gone so fast that, well, let me perhaps say...
Can you display the previous one?
Yeah, wait. So now... this is a difficult problem. So there's that there. But by the way, I mean, I guess these notes we will put up. They're just a summary of the other notes. They will put up on the website. And even the ones I... Remember, there is right and wrong in mathematics. Okay, so well, people can think about this. I mean, whether there's an analogous argument for elliptic curves that I think it's true for any elliptic or any abelian variety over a number field. And you took such a ZP extension, I think it's not quite obvious, but I think the same sort of argument would show that the group of rational points now you're talking about rather than the units would be a free modulo torsion at the top would be a free abelian group. I think this is always true. There's no infinite divisibility or anything like that that can creep in when you take mod Ilve groups up an infinite extension, something which is not quite obvious. Okay, so now let me perhaps in the few minutes that I have left, well, I have 15 minutes left. Is there anything that's been, have I gone too fast? Is everything, sorry?
5 minutes. 5 minutes.
Oh, 5 minutes left. Oh, my God. Okay, well, let me see what I have to say next and say a word about it. So now, I mean, the whole idea, let me say that we're going to prove, I won't have time to prove it now, but I'll just tell you what happens, that we'll show by using this type of result that for all n greater than 0, we have an exact sequence En prime tensor QP mod ZP. We, in some sense, look at the analog of what I've been talking about now when you tensor with QP mod ZP, and you get then into E infinity prime tensor QP mod, whoops, is that a... And then the co-kernel here, that's what's interesting, is H1 of gamma n acting on E infinity prime. Now, this By the way, here's fixed by gamma n, of course. This sequence, which is the heart of the proof now, is not obvious, and I'll be talking about its proof tomorrow morning at 9 a.m. in detail. But let's just notice that if you have that, then, and if in addition you can show that the H1 of gamma n E infinity prime is a finite group, that there's no ZP rank in that, then you're home. This is Iwasawa's observation, because you see, we know exactly how big this group is here. So we know the number of copies of QP mod ZP in E infinity prime tensor QP mod ZP gamma n. So that means if we take the compact dual, we know the number of copies of ZP in the gamma co-invariance of the HOMs of this into QP mod ZP. And that will give us our theorem. So everything hinges upon this, proving this sequence here, and you can think about it yourselves. It's not quite obvious at all, but it's not all that difficult, and I will prove it first thing tomorrow morning, and then we will see, and then we'll show also the finiteness of this, that we have the theorem. Thank you very much.
Any questions? I'll ask. Okay. Well, let's thank our speaker again.